The periodic table and atoms. Well, the structure of an atom, in the center of an atom, you have your protons and your neutrons. The protons have the positive charges on them. The neutrons are neutral. They're the little red ones down here. And then you got the negatively charged electrons spinning around the atom here in the electron cloud. Sometimes they draw it like this as a Bohr model, where they put rings around it showing about where those electrons might be located. The first ring can have up to 2 electrons on it, and then when you get over 2, you have to create a new ring, and then the second ring can have up to 8 electrons on it, and then once you get to 8, that one's full, and you have to create another new ring, and that one can have up to 8 as well. So in this case, we have 3 protons, and then we have 3 electrons. For every positively charged proton that you have, you need to have a negatively charged electron floating around it out here. We got 1, 2, 3 electrons. We have 1, 2, 3 protons, and that keeps everybody happy. It's all nice and balanced. Of course, we categorize our elements based upon the number of protons, and that is the atomic number that we have up here. We see lithium, and the fact that lithium is number 3 on the periodic table, that tells me we have 3 protons in it. That's what that number 3 means right there. But because we can assume there's also 3 electrons around it, we can also use that number to kind of determine the number of electrons that we have floating around lithium as well. Now, the atomic mass here on the bottom, we always round that. The atomic mass here would be 7. And what that is that's the number of protons and neutrons in the nucleus. Now, right here, this one is showing 6. Let's just draw another neutron in there, make it look like it should look. Okay, so this is going to be another little neutron in there. What we're looking at here is we have 3 protons and 4 neutrons, and they add up to the number 7. That's what the atomic mass is. And that's why you can do the trick for finding the neutrons. I always say Jimmy Neutron loves math. So the protons and electrons, you just use this atomic number, but for neutrons, we have to do a little math. That's where you take the bigger number and you subtract the smaller number. So in this case, I take, of course, we round it first, and we have 7 minus 3, we take equals 4. What we did there, to find the number of neutrons, we took the atomic number 7, and we subtracted the atomic mass 7, we subtracted the atomic number, and that left it with 4. Because what we're doing is we're taking the atomic mass, which is the number of protons and neutrons, and we're subtracting the atomic number, which is just the number of protons. We're just taking this whole thing and removing the amount of that's protons, and that leaves behind just the number of neutrons there. That's why that little math trick works. The periodic table is laid out. We have the families run up and down. And we have the alkali family, alkaline family. These are our transition metals right here. We have our boron family, which is the element that's at the top. The carbon family is these guys. The nitrogen family, the oxygen family. Then we have the halides, or the fluorine group right here. It's not called the fluorine, it's called the halides, or the halogens. I always say Master Chief likes to brush his teeth. So like the video game Halo, and we think of fluoride, we think of toothpaste. So the halogens are going to be this group next to the end, and of course the noble gases are the ones at the very end. So those are going to be your families or groups. Families or groups, they have things in common like any family does. That's why they are one underneath each other on our little families right here. For instance, the noble gases are all unreactive. They're inert gases. They're not reactive at all. The alkalis are extremely reactive, and so they're all kept in this little family right here, the alkali group. Drop them in water, they're explosively reactive. Things like the coinage metal group right here, we have copper, silver, and gold. They're all very lustrous. They're very malleable. They're metals. They're used in coins because of their properties. And so families all have the families are similar characteristics to them. All right. So then we also have our periods run across the periodic table. We have period 1, period 2, period 3, period 4, 5, 6, 7. And that tells us how many rings there are around our little atom here. For instance, let me go up here. we've got 1, 2. I'm marking my valence electrons here. All right, we skip over here. It says 3 valence electrons, 4, 5, 6, 7. And then this salt group has 8, except for helium only has 2 valence electrons. So what this does is, say if I was to pick lithium up here, which we were working on before. All right, lithium is in the second period here, so it should have 2 rings around it, which it does have 2 rings, and it's got 1 valence electron, which this has 1 valence electron around it as well. This is kind of like a seating chart, where if for the first ring that I have, I can only have 2 electrons in that first ring. And so hydrogen and helium, hydrogen's got 1 valence electron, helium's got the second. After that, I have to add another ring, because that first ring can only hold 2. So that's when you jump down to the next row. So these are going to be all the ones that fill up the second ring. So here's my second ring, and as I keep going across the periodic table, I keep adding. Beryllium will have 2 valence electrons. Boron will have 3 on that second ring. Carbon will have 4, 5, 6, 7. Neon will get up here, and you'll end up having 8 valence electrons on that ring. 1, 2, we'll keep this one, 3, 4, 5, 6, 7, 8. When we get to helium, well then after neon, once we get to neon, we can't put any more electrons on that second ring, so we have to draw a new outer ring, and that's when you would go to the third row on the periodic table and start filling it up with 1 valence electron on the third ring, 2 valence electrons on the third ring, 3 valence electrons on the third ring, 4, 5, 6, 7, 8 when you get to argon, and then when that one's full, you'd have to start a 4th ring around it. So the period tells you how many energy levels or orbits or rings are around that electron, and then the family that it's in will also tell you how many valence electrons or how many electrons are on that outermost ring, however many rings it does have.